At the edge of the solar system, our most distant planetary neighbors slowly make their way around the sun. Even though they form from the same swirling nebula as all the planets, the incredibly cold temperatures on the verge of deep space shape these worlds and their moons in ways we never expected. Voyager 2 brought us our first close look at these mysterious places, beginning with a blue-green giant discovered by chance just 200 years ago.
The planet Uranus was the first to be found in modern times. It was discovered by the English astronomer William Herschel. It was a wonderful and remarkable discovery because he was trying to do something entirely different when he stumbled across this object.
He didn't realize it was a planet. He thought it was a comet. He published a note on it as a comet. But as its motion was examined by others, it was realized that indeed he had discovered the first planet in historical times.
Once you discover a planet, of course, you have a problem on your hands, and that's what to call it. This wasn't a problem in Herschel's mind, of course. He was indebted to his patron, George III of England, and so it's clear. Let's name it after King George. He wanted to call the planet Georgium Sidus. In fact, he proposed that, put it in writing and all, George's star. That notion, however, didn't sit well with the international astronomical community. In time, people finally settled on just remaining consistent with the system that was already in place. All of the other planets were named by the ancients. They were gods of the Greco-Roman tradition, and so it was appropriate then simply to name this planet Uranus, at that time the farthest planet from the sun, and so Uranus after the god of the sky or heaven.
In 1986, over 2 centuries later, Voyager 2 visited the cold outer regions of the solar system, sending us astounding images of the god of the sky.
With Uranus, we get to, if you will, the Uranus-Neptune pair, which are two smaller gas planets that are considerably smaller than Jupiter and Saturn. They're made out of the same basic materials, that is hydrogen, helium, methane, ammonia, and so forth.
The interiors of Uranus and Neptune are rather similar, and we think that they have much more ice than Jupiter and Saturn, or indeed of any planet in the solar system. So we could truly call them giant icy bodies.
They don't have surfaces underneath, but as you go down, they get very dense. You probably have the same types of materials that make up rocks here on the Earth, silicon, oxygen, iron, magnesium, all compressed along with the gases and the materials that make up ice in a, if not a core, at least a very dense area inside both Uranus and Neptune.
While the two outer giants have a similar composition, a twist of fate has made Uranus an odd brother in the Jovian family.
Most planets, as they go about the sun, have roughly keep their orbital axes sort of roughly perpendicular to the plane in which they orbit. Uranus has this very peculiar property that its orbital axis is tipped such that it is nearly in the plane of its orbit.
Of course, in the case of the Earth, there is a tilt, and that's responsible for seasons. In the case of Uranus, remarkably, that tilt is very large indeed. It is so large that it is more than 90 degrees. We think that perhaps the reason why Uranus has this unusual rotation, tipped over on its side, is because it was hit by a large body as it formed.
So for the whole period in which Uranus goes around the sun, at one point, one pole of Uranus is pointing toward the sun, the other pole stays in the cold for many, many years. As it goes about the sun, half of that orbit later, the other pole is fully illuminated.
And it just so happened that when Voyager got to Uranus, the sun was almost directly overhead at one pole. And so that raised the question, what kind of weather patterns would we see? Would the distribution of sunlight completely alter things? Or what turned out to be the case, Uranus turned out to be just a tipped-over version, as far as the weather patterns were concerned, of Jupiter and Saturn and Neptune. In other words, the spin of the planet controls the weather patterns, not the position of the sun.
Visually, when you look at Uranus, you might conclude that it's totally different from Jupiter and Saturn. As we got more detailed measurements with Voyager, we found, yet again, the cloud patterns and the atmospheric patterns were there, but very, very subdued in contrast. There's in effect a big screen or haze layer above those cloud decks, causing them to be very difficult to see.
Deep beneath this thick layer of haze, the interior of Uranus churns, producing a characteristic feature of the blue giants.
Most of the planets that we've studied with spacecraft so far have got magnetic fields, and most of them you can think of as being pretty well behaved, that the planets are oriented like this, spinning like this, and the magnetic fields are pretty simple. They're aligned with the rotation of the planet.
When we got to Uranus and Neptune, we found that they too had magnetic fields, and relatively strong magnetic fields, but their major difference was that they were much lumpier, if you will, than the fields of Saturn and Jupiter. And in fact, the fields weren't even on the main axis of the planet in those cases.
Now, for Uranus, we have some understanding why it might be weird, because the whole planet is tipped on its side. So that we thought made sense, but then Neptune came along and it's not tipped on the side for rotation, but the magnetic field is weird, so we don't have a good explanation for either of those two planets now.
While the tilt of Uranus did not produce its strange magnetic field, it did affect the debris surrounding the planet, an off-kilter carousel of ice and rock.
The rings of Uranus were actually discovered from the ground as astronomers watched Uranus move in front of background stars, measured the brightness of the stars, and saw that the stars flicked on and off a few times before they got covered up by Uranus, and then flicked on and off a few times as Uranus moved away.
The fact that these blinks were sort of like a mirror image of each other, they were part of an overall pattern, suggested that what we were probably seeing was a complete ring and two opposite sides of it that were blocking out the light of this distant star.
It was very quickly recognized with some quick calculations that the reason we couldn't see them must be that they were very dark. That is, they were not bright ice particles like we see in the rings of Saturn. And this is, if you will, one of the themes about Uranus. Uranus seems to be a system that is relatively dirty.
The nature of the material that exists out there, we've seen some of the darkest material we've ever seen. The ring material and some of the moons have reflectivities of only a few %. That's half the light reflected off soot.
And that darker material probably is a mixture of rock, dark rock, and dark carbonaceous material, hydrocarbons, such as we see in very primitive meteorites.
One of the odd things about rings that we're seeing in almost all the planets are that they don't seem to have very long lifetimes. The dust in Uranus's ring tends to get swept out very, very quickly in a time scale of tens of thousands of years. That's very, very short compared to the 4.5 billion years, which is the age of the solar system. So what we're seeing today is probably something that would have looked very, very different a million years ago if we had telescopes and were looking at Uranus. And perhaps what we're seeing in the ring systems are just a local event, the last few collisions that have thrown out dust and debris around these planets.
Beyond the dark rings of Uranus circled the planet's diverse collection of moons, a visual record of our early solar system, frozen in time.
Planet Uranus has a wonderful family of satellites. Many of these were discovered by the Voyager spacecraft in 1986, but we knew about 5 of them from telescopic observations that had been made from Earth in the preceding many, many years.
The strangest thing we found around Uranus was probably the moon Miranda. Here was a moon that appeared to be assembled almost like a jigsaw puzzle of terrains, kind of squashed together.
The object itself is round, but the surface was the most disturbed surface that we had ever seen. And this disruption did not look like it could have happened from just the continual process of bombardment by small objects striking the surface. There was something else that happened to Miranda.
It's as though somebody took several different objects and broke it up and then put it together again, so that you had bits and pieces of things that have different history. Often when we see an object close in, we suspect that tides are important. In this particular case, it's not clear that tides could produce the effect. It has been suggested that Miranda might be a reassembled body, that there were some large impacts early in the history of Uranus that broke up a satellite, and then it reassembled to produce this hodgepodge that we now see.
What Miranda's telling us is something that we're starting to see again and again in the outer solar system, and that is that objects form, moons form in close to planets, and they tend to break up. We believe that the ring systems that we're seeing are probably the remains of moons that have been destroyed around these planets. And also we're seeing moons like Miranda that were broken apart and reassembled. So it's telling us that the history is very, very violent in these areas near the large planets.
An interesting thing about all of the satellites of Uranus, including Miranda, is because when Voyager got there, their south poles were pointed directly toward Voyager and directly toward the Sun. We only saw half of each one of these objects. The entire other half of the satellite was hidden from view in the night side continually while the Voyager spacecraft was there. So we've only seen half of these things, and it's fascinating.
After its brief survey of Uranus and its many moons, Voyager 2 journeyed on to the next planet of the outer solar system, the first to be predicted before it was observed.
In the next century after the discovery of Uranus, there was a growing suspicion that there might be another planet beyond the orbit of Uranus. And this suspicion was prompted by recognition that Uranus, while obeying the laws of gravity, was also kind of not obeying them exactly as expected.
It didn't follow the trajectory that the celestial mechanicians thought it ought to go on. And as a result, several people set to work to see what another unknown planet lying beyond Uranus would do to its motion. And they were able to establish where such a planet should be. And it was almost immediately discovered. It was seen as a great triumph for the Newtonian mechanics.
In 1989, a century and a half after astronomers first plotted Neptune's path, Voyager 2 arrived to survey a second blue giant.
The blue-green color of Neptune is quite similar actually to what we see also at Uranus. The average color, if you will, is about the same. And the reason is that the heavier gases, particularly methane, are more abundant in its atmosphere than hydrogen and helium. And the colder temperatures also affect how the gases reflect sunlight. Methane absorbs red light very, very well. And so they appear to the eye a relatively pale blue-green because the red light's gone as a result of methane absorption.
Neptune and Uranus are alike in many respects. There is one striking difference. When we look at the atmospheres, Neptune has features that stand out in a way that Uranus does not. The bluish surface of Neptune has some cloud features, including a spot.
The largest visual feature in the Neptune atmosphere is the so-called Great Dark Spot. It's of a scale that's significantly smaller than the Great Red Spot on Jupiter, but it's still much larger than most of the weather systems that one sees on the Earth.
Several of the giant planets have spots. We see these because of their differences in coloration compared to the surroundings, but actually the more important feature is the circulation, the flow associated with them. In fact, they seem to be vortex-like structures, vortices, just like the flow down a plug hole when you let the water out of the bath. It's not clear why Neptune has these features and Uranus does not, but certainly Neptune has some very strong winds and some cloud features that we can track and try to understand.
After surveying Neptune's winds and storms, Voyager turned its instruments to the planet's faint rings.
The rings of Neptune were discovered in a manner similar to those of Uranus, and those observations immediately sparked a tremendous debate, because with Uranus, everything was nice and regular. At Neptune, what happened, you saw the star flick off on this side, nothing happened when it got to the other side. It got the dynamicists thinking about new models of rings that weren't complete arcs all the way around the planet, but in fact had kind of horseshoe orbits where you had so-called ring arcs. As we got to Neptune with the Voyager spacecraft, we found that yes, indeed, the rings did go all the way around, but they were so thin that the starlight just wasn't absorbed at all as the material moved in front of the star.
Planetary scientists speculate these ring arcs are formed by the gravitational influence of small satellites, tiny members of a family that also include a cold and curious moon.
The coldest place in the solar system currently is an eerie moon around the planet Neptune called Triton. It is so cold in the Neptune environment that gases which we normally always think of as gases have a chance to solidify and become snow and frost.
Triton is an icy object which is comprised in some part of water ice, but it is coated with a surface of frozen nitrogen. Now, nitrogen will only freeze at the very, very low temperatures of the outermost parts of the solar system.
In laboratories, we can have liquid nitrogen, but here we're talking about so cold that you have nitrogen frost. Also, methane, swamp gas on Earth, becomes so cold that it becomes frost.
As Voyager 2 swiftly approached Neptune, our perception of its largest moon dramatically changed with each incoming image.
The first thing that we noticed was that Triton didn't seem to be as large as we had previously thought, because we thought it, in order to reflect that much light, and since we figured the surface was kind of grayish or darkish, it had to be a pretty big object. And the radius of Triton kept getting smaller and smaller in the calculations because the surface reflectivity kept getting higher and higher. And now we find, when the Voyager spacecraft gets to the Neptune system and actually flies by Triton, it looks at the surface and finds that it's astoundingly bright. Well, what does an astoundingly bright surface tell us? It tells us it's probably a new or a young surface in geologic time.
We see some surfaces that appear to be volcanic, although in this case the fluid is clearly not liquid rock as on the terrestrial planets, but perhaps water, or maybe even a mixture of water and ammonia, perhaps even involving methane. We see in addition some remarkable corrugated terrain, actually called cantaloupe terrain by some people because it looks like the mottled surface of a cantaloupe. And that terrain too, we suspect, is in some way volcanic in origin.
As scientists studied the Voyager images, they came to a startling conclusion. Even today, frozen Triton is being resurfaced by active geysers.
How does Triton get to have the heat necessary to maintain some kind of volcanic or geyser-like activity? This is, again, unexpected. Objects that small, again, objects the size of the moon, should not have enough internal heat generated within them to cause a volcanic-like process. Well, there's something that's unusual about Triton in its relationship to Neptune.
It is in a retrograde orbit, which means that it goes in the opposite sense from most orbits of planets and satellites, also in a very inclined orbit compared to the plane of the equator of Neptune. Certainly the unusual orbit of Triton suggests an unusual origin, and people think that Triton was captured.
If the object came in and was captured as sort of a tramp object rolling around in space and was captured into Neptune's orbit in recent time, then it received a burst of tidal energy from that Neptune encounter, which heated it up inside a second time, causing it to slowly cool off and to boil away, and we still may be seeing some manifestations of that.
Part of the behavior of Triton is more just the fact that as you go further out in the solar system, you encounter these more volatile ices, these ices which have lower melting points, lower sublimation temperatures. They're more able to be broken down.
Materials that we think of as gases here on the Earth, like ammonia and methane, can mix with water to form ice mixtures which can melt at much lower temperatures than pure ice by itself. So if we have even small amounts, like a few percent of those materials mixed in with the water ice, then radioactive heating, a little bit of tidal heating, can get it up to temperatures that we'd still think of as very, very cold, and yet still allow the materials to flow over the surface, to deform, and to give you the prospects for driving interesting geology, even on these moons that are in deep freeze.
Another icy body, similar to Triton, patrols the edge of the solar system. Neither a Jovian nor a terrestrial world, this tiny planet has puzzled astronomers since first discovered just over half a century ago.
The American astronomer Percival Lowell was interested in the possibility of another planet, one more distant than the planet Neptune. And he based his belief in that planet on additional discrepancies that seemed to remain in the movement of the planet Uranus. So solving the problem again of the gravitational influence on Uranus, he predicted where a more distant planet ought to be found. Lowell did not find that planet. That task, in a sense, was left to another astronomer, Clyde Tombaugh, working at the Lowell Observatory.
I was so thrilled when I ran onto this thing that then fortunately I had the presence of mind to look at my watch and thought this might be quite historical. I ought to record about what time. So it was right about 4 o'clock Mountain Time on 18th of February 1930.
It was discovered in 1930, and astronomers have been watching it ever since, trying to understand what it's made of, how it might have originated, and what it can tell us about the formation of the solar system.
Pluto's the only planet in the solar system not explored by a spacecraft. Voyager couldn't get there in its grand tour. Pluto's the Mount Everest of planetary exploration. It's the smallest, the hardest planet to get to. It's a very, very tiny point of light. It's not resolved at all in ground-based telescopes. What we do is we measure spectra in the infrared and the visible, try to determine what it's made out of. So far, we've discovered nitrogen, methane, carbon monoxide, and water.
Very little else could be known about it, and we thought that we were going to be stuck in that situation observationally for a good many years. We were given a very interesting set of circumstances that happened quite fortuitously, which occurred a few years back. It was discovered that Pluto had a moon.
We were very, very lucky that shortly after its moon Charon was discovered, we found out that the Earth was going to pass through the plane of its orbit. In the late 1980s, that occurred, and a set of eclipses happened where the moon Charon passed in front of Pluto, blocking systematically portions of the planet. We were able to map it. We were able to learn a great deal about Pluto-Charon system at that time.
Pluto itself is smaller than our own moon, but its satellite is roughly half the size of Pluto. And there is a unique tidal locking of Pluto and its satellite such that each object keeps the same face directed at each other throughout the entire rotational cycle.
Even with the insights provided by the eclipse of Pluto, astronomers have yet to account for the origin of this distant outpost.
Pluto's an oddity to explain. We've got the terrestrial planets in the inner part of the solar system. We've got the gas giants further out, and then we've got Pluto, which is a very, very tiny world existing outside the orbits of these gas giants. The challenge is to explain this. we now believe that Pluto is probably an end member of a large population of material, and what we're looking at are the materials left over from the formation of the planets.
We call them planetesimals, bodies of many different sizes, including comets even. These objects were formed by comets colliding with each other. Some of them got cast out of the solar system completely. Some people feel that there may be objects like this further out than Pluto.
Astronomical objects beyond Pluto often are given the hypothetical designation of Planet X, and Planet X observations have gone on for years based on the search on the idea that the farther out you look and the better your instruments are, that sooner or later you'll find something. But that we would probably not expect to find something the size of Jupiter or Neptune or Uranus or Saturn out in that area of the solar system. That much we can rule out.
In recent times, we have seen some objects beyond the orbit of Pluto, objects that are perhaps 200 kilometers across, so they're considerably bigger than comets, and we are starting to see more of them. Who knows, perhaps there are even objects the size of Pluto further out, yet to be discovered. The further out they are, the harder they are to see.
Nearly 40 times our distance from the Sun, Pluto remains an icy, enigmatic neighbor, the last in a fascinating family of outer worlds. Born of the same basic elements, each obeys the same physical laws, yet their distance from the Sun forged them in dramatically different ways. By exploring these differences, we learn more about our solar system and our place in the infinite frontier.